This is what's known as acid catalyzed epoxide ring opening, because don't get confused, there is a base catalyzed epoxide ring opening. And we take our epoxide and we get a 1,2 disubstituted glycol, so a diol. Now it's important to remember with the acid catalyzed epoxide ring opening, we attack at the most substituted position. As you can see here, we attacked right here to open that ring, and we kick this up. This is a backside nucleophilic attack. So if there is stereochemistry here, which there should be if it's on the substituted side, we will get an inversion of stereochemistry. If they're equivalent, you're going to get a 50-50 chance it attacks either side. But let's walk through that mechanism right now. So our oxygen is going to get protonated by our acid. Remember, this is just generic acidic conditions. We're using H3O plus for that. If you're unsure of where H3O plus comes from, check in on your acids and bases. And we are going to get this protonated epoxide, where oxygen has a positive charge. Like that. That's a tiny, we're going to roll with it. Has a positive charge right here. And then we have water now, because this was H3O plus and it lost a proton. It's going to attack at our most substituted position. We're going to kick these electrons up here. We're going to form now. It looks like this. We have an extra proton here with a positive charge, and we inverted that stereochemistry. And then we're going to have another H2O plus come here. We're going to take this. We're going to kick the electrons up here. We're going to make our final product, and we regenerate our acid catalyst. Now, why does it attack at this most substituted position? Well, let's draw two different scenarios where if we were to draw a resonance structure, so to speak, of this right here. Okay, one where we break this bond, kick the electrons up, one where we break this bond, kick the electrons up. In this one here, we have a primary carbocation, very unstable, actually like the most unstable carbocation you can have. In this one, what do we have? We have a secondary carbocation, more stable than the primary carbocation. Now, this doesn't proceed through a carbocation mechanism at all, but what it is that this is more stable. So this carbon has more of that carbocation character, so to speak. So while this oxygen has a positive charge and a partial positive, it's pulling electron density from these carbons to try and compensate. So this has a partial positive. This has like a more partial positive. It makes it more prime for that nucleophilic attack, which is why attack happens there. Now you can also do this with an alcohol. So we'll say H plus, and we'll say ROH. Just keep it a generic alcohol. What's going to happen? You're going to go through the same mechanism, except now you're just going to make an alkoxy ether, or not alkoxy ether, alkoxy alcohol. It's an ether and an alcohol. That's what you're going to do. And so yeah, that's too easy. And then so also you can do this with HX, like halogen acids, so like your HCl, HBr. And initially what that does is it forms this product right here. But then you're going to end up dehydrating this likely to put it right back, and you're going to form your dihydrogen, or not hydrogen, dihalide. Ugh. And there's just way better ways of forming that, so it's not really a synthetically useful transformation. So if you enjoyed this video, be sure to hit that follow button and get some more organic chemistry learning.